Hi, my name is Adarsh. I am a student researcher at the MIT IBM Watson AI Lab. I will be presenting our work Select Level and Mix for Partial Domain Adaptation. Unsupervised Domain Adaptation or UDA, which aims to adapt models trained on a labeled source domain to a completely unlabeled target domain, has attracted much attention in recent years. Partial domain adaptation, which is a more practical and challenging variation of UDA, has the categories in the target data as a proper subset of that of the source data. Trivially aligning the two domains with this setup can adversely affect the performance of a model because of the presence of the outlier categories. More recently, prior works have attempted towards solving partial domain adaptation by training domain discriminators with weighing or have used reinforcement learning to learn source selection, but they are tedious to train. In this work, we dissect PDA and address the three major problems, which are negative knowledge transfer because of the outlier categories, lack of discriminability in the target domain owing to the absence of the labels, and domain invariance in the latent space for robust representation learning. We propose three unique modules corresponding to each of the problems called select, label, and mix. Now let us look into each of these modules. First, in the select module, our goal is to learn selection of the relevant source samples to avoid negative transfer. We achieve this by employing a selector network which takes source samples as input and maps them to a discrete binary output space of either 0 or 1, meaning either discarding or selecting a sample. The discrete output space makes optimization through gradient descent difficult because of non-differentiability, because of which we use the Gumbel softmax trick, which uses softmax relaxation of the argmax function to approximate the gradients for backpropagation. The supervision to the selector network is provided by designing a triplet loss function, which tries to minimize the distance between the selected source samples and the target samples, while maximize that between the discarded source samples and the target samples in the feature space as shown here. The selected source samples are then passed on to the further modules. The label module aims to provide discriminability to the latent space by harnessing self-supervision from the target domain. This is essential because the absence of label data in the target domain does not provide any class-aware information to the models. We use soft pseudo-labels instead of one-hot pseudo-labels to avoid false and noisy predictions. Discarding the outlier source samples results in a decrease of available labeled data. To address this, the mix module incorporates interdomain and intradomain mix-up, which leverages training on convex combinations of samples to promote domain invariance and learn robust representations both across and within the domains. The mixed samples are used for both the classical and the domain discriminator as shown here. Finally, here is the complete framework where we have in total 4 networks. Each of the 3 modules are trained end-to-end jointly and leverage the interactions between them for partial domain adaptation, which is simple and easy to train. We perform experiments on 4 benchmark datasets, and we use ResNet 50 and ResNet 18 for the feature extractor and the selector network respectively. Coming to the results, the upper half shows performance by UDA methods, while the bottom half methods are specifically designed for PDA. As can be seen, UDA methods underperform and are vulnerable to negative transfer. One of the most recent UDA method gives a mere accuracy of 88% on Office 31, while the recent PDA method BA3 US obtains an accuracy of 97.8%. Our SLM achieves the new state of the art with 98.4% and performs the best on 4 out of 6 tasks. On VCA 2017, SLM significantly outperforms the previous state of the art by 18.9%. For results on Office Home and Image Caltech, please refer to the paper. Here we show some ablations on the individual modules, and we also analyze the feature space based on Wasserstein distance, which corroborates the proper learning of the selector network to discard the outlier samples and avoid negative transfer. Thanks a lot.